Welcome back to our continued exploration of recursion in SQL. Hi there. This video is the start of a series on extended use cases on how to use recursion in SQL. So I hope that all of these use cases in itself are interesting enough just to look at the problem and how SQL and recursion in SQL can actually solve that problem. But of course, this is not a course about these particular problems. It's a course about SQL, advanced aspects of SQL, and in this part of the course, in particular, of about recursion. And also, these examples, I hope that you can understand them in a more abstract way, in a sense that there is a particular type, a particular category of challenge or problem that is occurring here. And there is a particular suite of techniques that you can use in SQL to address these particular problems. So maybe it's, after you've studied all these problems, maybe it's worth to take a step back and then look from a distance at these problems and try to see the general computation pattern that we've used in SQL to address these. Of course, I will point out these patterns, the bigger ideas that have been exploited to address these particular problems whenever we encounter these particular techniques and approaches. So I think without further ado, let's get into the whole thing. The first problem that we would like to study is graph related. All right, so let's go there. Here we are. So what would be typical for the following suite of videos and slides is this particular symbol. It's our use case symbol. And as I told you, all of these upcoming videos will center around a particular use case, and embodied in that is a general bigger idea about the usage of SQL and recursion in SQL. So let's see. Let's talk about graphs first, all right? So this would be an undirected graph of 7 nodes, and the edges between these nodes. You see that all of these nodes have been labeled from A to G in this particular case. Right, so what we try to address here is finding connected components in this graph. Okay, so this graph is comprised of, as you see, 3 partitions, C1, C2, and C3, which are in graph theory are also termed connected components. Inside such a component, each node can reach any other node by edge traversal along a path of arbitrary length. All right, so of course each node can reach itself, so E can reach itself, but no other node. So E is one node that makes up a connected component on its own, but F and G can reach each other, obviously, but no other node. So F and G make component C3, and A, B, C, D, they are connected to each other. I can travel from any node in component C1 to any other node, and as such, these nodes are part of component C1, but I would not be able to cross component borders here. Right, so this is what defines a connected component in a graph. All right, so what we would be given here is the representation of this graph, and finding C1, C2, and C3, and deciding the membership of any of these 7 nodes to each of these components. That would be the problem to solve here. All right. So obviously this is graph related. This is a graph data structure. We would have to compute or execute graph algorithms, and the answer is, well, okay, do I need a graph aware database system now? Do I need a DBMS that is tailored to process graph data structures and can solve graph problems? And well, there's many answers to this question, and there's a whole community in the database community that is focusing on the construction and optimization and the architecture of specific graph-based DBMS. But in this course, and as a number of colleagues out there and applications and companies are pursuing, in this course, we will just use plain relational database systems to store and process graphs, right? Because graphs are just edge relations, right? So these two nodes F and G are related by this edge between nodes 6 and 7. And well, relations is something that we, of course, can represent in our tabular-based and our relation-based database systems. Connected components are equivalence classes of the reachability relation. So there's a reachability relation that connects A with B and A with C and A with D, right? There's a reachability relation that partitions the set of 7 nodes that comprise this particular graph. And well, such reachability relation can be represented and computed by a normal relational DBMS. And that is exactly what we are trying to do here. You will see that the representation of graphs and also computing algorithms over graphs can be performed rather succinctly and elegantly in a normal tabular DBMS and SQL. Okay, so first, how would we represent this graph? It's an undirected labeled graph. So all the nodes carry labels. We have 7 nodes here, and there is one particular table, the nodes table, that would represent the labels of each of the 7 nodes. So 7 rows here, 7 labels have been assigned. I think that should be self-explanatory. Okay, then there is the edge relation. All right, I would start out with this particular relation here that we would then grow. You see that this edge relation talks about directed edges still. Well, this graph is undirected, but we would start with a directed view of the graph that would talk about the edge from A to B here, from node 1 to node 2. And this is exactly this particular row that's being represented here. So it's exactly this edge. Right. And we do this for all the edges. Actually, we pick some arbitrary direction in which the edge should point, and that would be represented inside our edges table. Of course, this gives us a representation of a directed graph. From that, it's a tiny step to a representation of the undirected graph, right? So this has 5 edges that we are representing here. The undirected graph would be represented like this. Well, there's many representations, but for the coming minutes, let's work with this representation in which we represent an undirected edge between 2 nodes A and B by 2 directed edges from node A to B and from B to A. Right. So this doubles the number of rows. The number of entries in the edges table doubles to derive this particular graph representation that, well, that reflects the undirected graph. So what we are representing here is actually this. So there is arbitrary direction we can travel between nodes A and B if they're connected by an undirected edge. Okay. So, and when we will look at the algorithms that we use to compute the connected components, we will look at this particular table to retrieve the node labels, and at this particular table to learn about the incidence of edges to nodes or the adjacency of nodes. Right. Okay, so much for the graph representation. I think that's rather straightforward. Nothing much to see here. Obviously, a tabular-based database system can represent graphs just fine. Okay, so how would we now compute connected components inside such a graph? So we need a query plan, which again is a general strategy to address, well, in this case, moderately complex problem on that we are given. Right, this is not the query plan that the DBMS query optimizer would output. Okay. So what I'm proposing here is to start walks into the graph, path traverses or edge traverses inside this graph. And we would not pick one particular node to start this walk from. We would start our walks in all nodes at the same time. We walk from all nodes at the same time. right? So it's real set-oriented thinking in this particular case. No node is special here. Every node will form the beginning of a walk through that particular graph. So for each node M, when I'm saying that here, that means for each of the 7 nodes A to G, I will do the following. I will start a walk from A. I will start a walk from C. I will start a walk from G. I will start a walk from every node that I can get. For each of these starting nodes, I will record which nodes I can actually reach. So from A, I will be able to reach B, that's obvious. But later on then, I will also be able to reach D and C. All right, so for our node A, that was the origin of this particular walk, I would record that I can reach B, I can reach C, I can reach D. That's what I'm trying to do with these walks through the graph. From node G, I can reach F. Okay, I can of course reach G myself. That's obvious, but I can also reach F and, well, nothing else. From E, I can reach E, but nothing else. Right. Okay. Once we've completed our walks, once we cannot reach any new nodes, so there's already some iteration going on, right? So we continue to walk through the graph as long as we can reach and find new nodes that we haven't discovered before. If there is no new node to be discovered, that would mark the end of this particular walking phase. Right. For each of the 7 nodes, we would then check the IDs of all the nodes that could be reached, and we would simply use the minimum or the maximum. But hey, let's use the minimum ID of all the reachable nodes. That value would be used as the component ID. And that's all there is to it. 2 nodes that can reach each other, like for example C and A here, 2 nodes that can reach each other will look at the same set of node IDs. They will compute the minimum of this set of node IDs, and they will of course reach the same or compute the same minimum node ID, and thus will be in the same component. The minimum node ID that could be reached during these walks makes up the component ID. All right. I think that's a reasonable plan and doesn't sound too complicated. Actually, all the recursion is happening in this first step when we try to walk through the graph. Of course, we have to take care that we don't walk into endless cycles. So starting from B, we would of course be able to walk to D, which can walk to C there, which can walk back to B. That's nice. So we could walk to D again. So that would be a cycle, and we could walk and walk and walk. We have to make sure that such endless cycles are detected and still lead to a termination of this walking phase here. But as we can see, the set-based semantics of recursion in SQL will deliver this for free. Okay. So once we have completed our walks and once we have collected all the node IDs that are reachable, right, we would probably end up with node ID sets that look like this. So for example, looking at node B here and the set of nodes that could be reached while starting a walk from B, well, we would of course find the node ID 2 here, which is B itself. We could reach A, we could reach C, and we could reach D. That makes up for this set of node IDs, the reachable node IDs of 2, 1, 3, 4. You see that all nodes in this component here, all nodes in this cluster, well, they would all compute the same set of reachable node IDs, which is of course obvious, right? Okay. So all of these would compute the same set of node IDs. We would find the minimum node ID in these node sets and would end up with, of course, 1 here and 1 here and 1 here and so on, and would assign component ID C1 here. Okay, so that's the idea of the second phase of our query plan. right? Node E can only reach itself and no other further node. So this is the minimum ID. So node E lives in C5 here, and F and G live in C6. Well, the numbering here is a bit unfortunate. We would end up with components C1 and C5 and C6. Well, this is not nice, but some post-processing would easily map these irregular or unfortunate component IDs to sane component IDs that just are named C1, C2, C3, or any other naming that we prefer. So that would be simple post-processing that we would perform. We could also extract the subgraphs, so the components themselves are mini graphs, subgraphs inside the global graph, and based on these component IDs, on the components node sets, to be specific, we could easily extract the subgraphs, of course. We will see that as a separate post-processing step when we look at the actual SQL code. All of this could be done once we've assigned the component IDs like described here on the slide. So I think it's time already to look at the SQL code that we could use for that. And of course, it will be a recursive common table expression with union-based, set-based semantics. There it is. All of this easily fits on a single slide, or maybe on 2/3 of the slide. I think it's a rather beautiful implementation that well, performs parallel graph walks. I think that's quite nice. So let's see. We will compute this particular relation, the walks relation, this binary or two-column relation. This will be computed, and as I told you already, it's a good idea to think in invariance when you think about such recursive common table expressions. So what does it mean if a particular row n, f, node, front actually, node, front is found in this two-column table? Well, the meaning will be that node f is reachable from node n while we perform these particular walks. This is the semantics of this pair nf. If it's found in this walks table, then f is reachable from n by, well, maybe a 0-step path, 1 step, 2 step, any step length would be fine, but f will be reachable from n. Okay, so let's see how we seed this entire recursion. Well, we would just look at all the nodes, all the 7 nodes that we have available, right? And we would record that each node can reach itself. Each node can reach itself. And well, so each node would be the start of the walk, and it would also be the front of the walk. How far we have walked so far? Well, 0 steps. So that would actually lead to these pairs n in walks. So every node can reach itself. That would be the seed or the start or the base case query Q0, as we've called it in our introductions to the recursion. All right. So then this would be the recursive part that is iterated. Okay, this recursive part would of course refer to the walks that we have performed so far, right? So in the first column of walks, we would find the starting point of the walk. In the second column of walk, we would find the front column. We would find how far we could walk from this starting node already, all right? To perform and then the next step in the walks, we will of course look at the edge information that encodes our undirected graph. That's the graph table that we've introduced a few slides back. Okay, so if I've already walked to the front node in my walk W, then well, I can extend this particular walk by looking at a particular edge that starts in this front node and leads me to the end of this particular edge, to its to node, right? So obviously, starting in this starting node, which is unchanged, I can even reach the end point of this next incident edge. All right, so this extends my walk by a single step, and that would be a new front node that I can reach while I started from this particular starting node here. And that's all there is to it. This would be new nodes that I've discovered, and they would be input to the next iteration of our evaluation of this recursive part of the query. Of course, because we are performing the computation in the union or in the set-based semantics, only nodes, only front nodes that we haven't discovered before would be recorded. Anything that we have reached before, any node that we have reached before, would not be considered a new row, and it would be removed from the further consideration during my iterative query evaluation. This is exactly what we need to avoid walking into endless cycles. Once I have found that I can walk from A to D, I will never consider the knowledge that walking from A to D is possible ever again. So I will not walk into endless cycles. This is all we need. This is the database system, and its recursive SQL set semantics is actually giving this cycle detection and cycle removal. It gives it for free here. That's nice. And I think that's all there is to it. That's a tiny piece of code and obvious semantics, I would say. Let's trace what's happening here when we compute this recursive CTE. This would be a trace of the entire thing. Okay, so that would be the input graph, just to remind you of that. In the first step of our recursive CTE, in the Q0, in the base case query, we would emit this partial result here. Right, so any node can indeed reach itself by performing a zero-step path. That's the seed of our recursion. And you can see that even the node E that can only reach itself is being recorded here, which is really important. We won't forget E here. Okay, so in the next iteration, we would of course follow the edges of the graph. So A can reach itself. Q0 has told us so much. Of course, A can reach any node that is recorded in the graph relation. So, well, A can of course reach B, B could reach D, and B could reach C. So what we see in the first iteration is just the graph relation, the 10 rows of the graph relation that that the system discovers here. Okay. Right, so these are the 10 nodes. These are really the 10 new nodes that have been discovered in this first iteration, and they would be added to the nodes that we have found so far. Okay, in the next iteration, well, in the first iteration we already traveled from A to B. Now we can travel from B to C using the BC edge here to make this path one step longer. So 1, 2, 3, that would be a new knowledge, a new endpoint of the walk starting from A. And indeed, we find it here. It's this particular row here, the 1, 3 row. Of course, we would also find that we can go from 2 to, from 2 to 3, we have found that before. Okay, so let me, we can even go from 1 to 4 here. We can go from 1 to 4, and we would find this in the second iteration. All right, so this is what we found here. Okay, we of course find the reversal of these traversals. We find them also, and all of this is new knowledge that would be appended in the second iteration. But as you can see, already in the third iteration, for the tiny graph that we are currently inspecting here, already the third iteration wouldn't find any new interesting traversals here. So walking from 1 to 2 to 3, we could of course extend our walk to D here, to the 1, 4, to form the 1, 4 walk. But we knew this already. 1, 4 was already known knowledge, and it won't be included in the result of the third iteration. Indeed, no row is included in the result of the third iteration, because everything that was known already has already been found. So that marks the end of our computation. And well, the union of all of these tables, that would be the result of our recursive walk. Well, the other the other steps of computing component IDs from this particular data, I can show you in the SQL file in the terminal in a minute. But this is non-recursive post-processing of the entire recursion output here, and would only mark the finalization of our results. So let's switch over to the terminal here. I brought the example with me, of course. This example talks about the same undirected graph that I've already shown you on the slides. So let's first create its relational representation. So we need an edge and a node table. All right, let's create these. Okay. Right. So this is the edge table that still talks about directed edges that are leading us from one node to another. Well, we will post-process this to form the undirected representation of the graph in a minute. Okay, so we were talking about these 7 nodes, and their labels are inserted here. Okay, and we were talking about the directed edges. Of course, for example, the node leading from F to the edge leading from F to G here is being included in the edges table, but in a second we will add the reversal of the edge, and together they will represent the undirected edge between the 2 nodes. Insert these. Well, let's look. First let's compute the undirected graph. So the undirected graph has, of course, all the directed edges that we have added, and all the reversals of the edges. So we would look at the edges. What is the target node will become the source node. What is the source node will become the target node in the edge reversal. And well, everything will be thrown in one pot. This is the representation of our undirected graph. Let's look at this. It's the 10 nodes graph table that you've already seen on the slides. So from node A, we can go to node B here. And we can also go from B to A. All of the, both traversal directions are included. This is the representation of the undirected graph. All right. Okay, now it's already time for the recursive CTE. And there's nothing new to see here. This is just the vanilla recursive CTE you have just seen on the slides. So nothing new here. Okay. And then there's some post-processing going on here, computation of the components. Let's not look at this at this particular point. Let's just look at the output of the walks that we can find. And as you can see, this is exactly what I'm emitting here. Just the contents of the walks table. So let's see what the phase 1, the recursive walks, give us. Okay, so indeed the computation terminated. Wonderful. All right, so from node 1, that's node A, we can reach node A itself. We could reach B and D and C. All of these are reachable, and that's about it. All right, so that's what we expected. It looks very much the same for the B node, the C node, and the D node here. This is already some indication that they probably will be in the same component. 5, node E, the solitary node E is of course recorded here. And it's very important that we don't forget it. So let me make this comment that it's very important to start the recursive computation by looking at the 0 step, path that leads from node to node itself. So that a node that is disconnected, like the E node, is not being forgotten. If you start your computation with the incidence relation, with the adjacency relation graph here at this particular point, E would not occur in it and would be forgotten. All right, so that's the reason why we start with the 0 step path here. Okay. Okay, so that would be the output of our walks. So from that, it's very easy to compute the component IDs. We would just look for each of these nodes. For node A, for example, we would look at all the reachable front nodes and would compute the minimum node ID there, which of course would be 1. Okay, so node A would be in component 1. Right, so let's look at this. Well, node B can reach these 4 nodes. The minimum component ID would be 1, so node B is in component 1, and so forth and so forth. This is, of course, a very simple application of grouping. Just the application of grouping and the minimum aggregate. And that's what we are doing here. As you can see, when I try to compute the components, all I have to do is look at the walks, group them by node, and then compute the minimum reachable node, which will serve as the component ID. Let's look at this. So this minimal post-processing, let's activate it and then try it out. All right, so this is a 7-row table. Each node has been assigned to its component ID. Indeed, the first ABCD rows, they live in component 1, and well, the E node lives on its own in component 5, and F and G live in component 6, as expected. Okay, so that's actually the connected component computation done already. Everything else is post-processing for beautification here. Well, we could long for component IDs that read C1, C2, C3, for example. That's easily done by simply ranking according to this component ID. Assign ranks to rows according to this component IDs. Rows with the same component ID would be assigned the same rank. We would use dense ranking so that all of these guys receive rank 1. The next entry here would receive rank 2, and these 2 would receive the rank 3. So just a dense ranking, the simple window function that we've used so many times already in the course, would be used to assign sane component IDs here, and that's what I'm doing here. You see, I'm just looking at the components that I've found and will then just perform a dense ranking over the component IDs. This will give an integer. I will concatenate this with the C prefix here to form nifty component IDs that read C1, C2, T3. All right, so let's do that. Okay, that looks good to me already. This would be an acceptable component assignment of nodes. All right. What we know as a last step, we could also derive the subgraphs. Let me activate this. The subgraphs. So which edges are actually found in the individual components. Okay. So what would I do? I would just iterate over all the components. And then for each of these components C, I would consider all the graph edges that are in my undirected graph. Okay. And well, if that component ID is found in the either in the source or the target, node of the edges in my graph, well, then this particular edge would be part of that particular component. All right. So I'm also taking care here that components that do not have any single edge, like the component C2 of our solitary node E, would also be considered here. So any component that does not find a joint partner inside the graph relation here would still be considered and would still be represented in our subgraphs relation. It would just be recorded there with a null value, because this is the semantics of a left upper join. Any row C that cannot find a joint partner G would still be considered in the output. We would still see it here in the output, but well, since no joint partner can be found, these two fields would be set to null here. All right, so let's look at the result of the subgraph computation. And that's what we find there. Right, so in the C3 component, the FG component, well, these two edges would be found there. This is the edges in the C1 component, and this is the C2 component, which is edgeless. All right, so much for the post-processing here. Right, when you look at the file connected components.sql that I will of course distribute in the repository, you will also find a version of the recursive walks that includes some debugging information. Debugging information in the sense that these are the two original columns that we've included in the walks relation already, right? What you will now also find is this iter column, which will tell you in which iteration of this recursive walk did we encounter a particular node. So we started from node A. How many steps did we need until we encountered node D? This is something that you will find in this additional query. Just have a look at it. It's very simply designed. This is just a modification of the original walk. This post-processing just makes sure that we output the minimum number of steps that sufficed to reach a particular node from a starting point of a walk. So if we perform this query, then you will see that, well, to get from node 1 to node 1, well, this was already encountered at step 0. So every node could, of course, reach itself with 0 steps. But to get from node 1 to node to node B, from node A to node B, I'm sorry, we needed 1 step. To get from node 1 to node B, or from node 1 or A to node C, we needed 2 steps already. And this is what you can find in this particular sample query. I encourage you to play with that, alter that, modify that, look at the output, try to understand what's going on here. Let's disable the post-processing and enable the raw walks information just so you can play with it. I think that concludes our discussion of the connected components, the first graph algorithm that we considered in this particular lecture. I hope you get a feeling that a relational database system can indeed be a very elegant and quite nicely programmable graph DBMS. All right, so much for this. Many more cool use cases ahead. I hope you stay with us. See you then. Bye-bye.